Hi, this is Dr. John Bergdorf. In this video, we're going to explore the complex number system. And in particular, we're going to be looking at sets of numbers that we talk about in mathematics all the time and how they relate to one another, and introducing, for the first time, the concept of imaginary and complex numbers. So, on this page, you'll see some sets of numbers that look very familiar, and I want to just make sure we have the terminology that goes with them all. So, when we are first in kindergarten, we learn about the natural numbers, also known as the counting numbers. Those are the numbers 1, 2, 3, 4, 5, and so forth. And for abbreviation purposes, we call that set the set N. Now, N is often written just as an N, like it looks, but it also is sometimes written as sort of a stylized N that has two vertical bars on the left. Now, if you throw in the number 0 with the natural numbers, so you have the set 0, 1, 2, 3, 4, 5, then you are exploring what's called the whole numbers. Now, the number 0 was not fully defined, understood until well into the Middle Ages, but as one simple number, throw in that one extra number, you've got the whole numbers. And that's usually written with a W, although often that is a more stylized W, looking like that. Now, if together with the whole numbers, you throw in the opposites of all the whole numbers, the negatives of the whole numbers, then what you create is the set of integers. The integers go forever in both directions, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and so on in both directions. And because there are going to be several sets whose names begin with I, we elect to use a different letter for these. We usually use Z, and again, Z is usually often written, in a more stylized fashion with a double bar on that diagonal bit there. Now, the next set of numbers that we talk about is the set of rational numbers. Now, rational might be a word that implies all kinds of things when you hear about it in everyday life. We talk about a person being rational or an idea being rational. But rational actually, historically, just comes from the word ratio, which is a fancy word for fraction. So the set of rational numbers is basically the set of fractions. It's the set of all numbers that can be written as fractions, A over B, where the A and the B are integers, however, so that restriction is made. The A and the B need to be integers, and the B cannot equal 0. Cannot equal 0. That's important, because if the B were 0, you'd be dividing by 0. And that set of numbers is represented by a Q. Again, R would make more sense, but we need R for something else. And the Q is often also written in a stylized manner like that. So what are some examples of some rational numbers? Well, we could have, for example, 3 over 4. That's an integer in the numerator, an integer in the denominator. That's a rational number. Because the numbers in the numerator and denominator can be negative, we could have 2 over -5. Because a positive number divided by a negative number is negative, 2 over -5 is the same as -2/5. Essentially, you can move that negative sign up front. Look at this, 8. Is that a rational number? So at first glance, you might say, no, that's not a rational number. That would either be a natural number or a whole number. The key in the definition is this little phrase right here, can be. The set of numbers that can be written in the form A over B. 8 can be written as 8 divided by 1. And since you can write it as a fraction, that means that it qualifies as a rational number. Now, moving beyond that, we talk about also the set of real numbers. Now, this will kind of go off in a different direction, but we'll see how it comes back together. The real numbers it's the set of all numbers that, together with a unit of measure, can represent a distance between 2 points. So a distance between points would you ordinarily have a unit of measure, like an inch, a mile, a kilometer, a centimeter, something along those lines. Ignoring the unit, whatever the measure is in that system could be a real number. Now, 2 points could be, for example, 4 miles apart. So I could take the number 4 and say that's a real number. And you might say, but wait, 4 is a natural number, and it's a whole number, and it's a rational number. It's also a real number? Yes. So 4 actually would fit into all of these categories so far. 3 halves could represent a distance between 2 points. Maybe they're 3 halves of an inch apart, so that would qualify as well. Negative distance does make sense. In a sense, we're going to say that it does, in the sense that perhaps we're moving in an opposite direction. So negative 2 miles would be, for example, if I'm looking to the east, negative 2 miles could be 2 miles to the west. So we're going to allow for negative distance as well. But distances need not only be natural numbers, whole numbers, integers, or rational numbers. You could have a distance of pi. Pi, the number that you might be familiar with representing or represented in the formula for the area of a circle, for example. Pi can represent a distance. However, it turns out that you cannot write it as a fraction. You cannot write pi in the form a over b, where a and b are integers. Can't be done. But it still could represent a distance. Here's another thing that could represent a distance. The principal square root of 3, that does not turn out to be a nice whole number or even a rational number. It cannot be written as a fraction, and yet one could speak of a distance of the principal square root of 3 feet, for example. And I guess it makes sense also, since we've talked about negatives, we can even talk about, maybe the negative cube root of 17. That could also be a distance, again, in the sense of a negative distance, meaning in the opposite direction. So all of those are real numbers, but not all of them are rational numbers. These guys here can represent distances, however, they are not rational numbers, cannot be written as fractions. So we have a special name for them too. We refer to them as the set of irrational numbers. The set of all real numbers that are not rational, that cannot be written as fractions. Now, an easy way to distinguish between a rational number and an irrational number is to look at the decimal pattern that you have. Rational numbers have decimal patterns that either repeat or terminate. Oops, stray mark. Sorry about that. There, clear off that. Rational numbers have decimal patterns that either repeat or terminate. What do I mean by that? Let's say we look at the rational number 3/4, and we convert that to a decimal by dividing 3 by 4. 3 divided by 4 is 0.75. That's a decimal pattern that just comes to an end fairly quickly. 7 over 11, that's a rational number. If we looked at its decimal pattern, it looks like this, 0.636363, and that continues on and on and on forever. That's what we mean by a repeating pattern. Sometimes we write that by putting a bar over just the part that repeats. So 0.636363 going on and on and on can be written as 0.63 with a bar over it. Remember that a whole number can also be considered a rational number, and the repeating pattern, the decimal pattern for 8 is simply 8.0, and that definitely comes to an end. So that's what I mean by decimal patterns that either repeat or terminate, and any rational number can be written in that form. Irrational numbers have decimal patterns that never repeat and never terminate. So if I look at a couple of the examples I had on the previous page, pi, for example, if you write out a handful of decimal places, it is 3.1415926 535 89793 And I think you get the point there. This never comes to an end, and you can prove that it actually never forms a repeating pattern. You might say, well, what if it starts repeating now? It doesn't. It just keeps on going and going, no pattern, and it never comes to an end. That's what happens with an irrational number. The principal square root of 3, its decimal pattern is 1.7320508007 568877. And so even though in there you might see some patterns that look kind of intriguing, there's actually never a repeating pattern, and it never terminates. So rational numbers and irrational numbers together, they form the set of real numbers. Going back a slide. Now, you can see that that many of the examples that I've shown you fit one inside the other. A certain number might be both a natural number and a whole number, for example. You can draw a diagram of this that makes it really, really easy to see how things connect. For example, if I just draw a circle, I'm going to change colors. Hold on a second. I have a reason for this later. If I draw a circle to represent, say, the natural numbers, I can put in here some examples of natural numbers like 1 and 3 and maybe 9. Those are examples of natural numbers. All natural numbers are also whole numbers. The only difference is the whole numbers throw in the number 0. So I can illustrate this like this. It shows that all of the natural numbers are contained within the set of whole numbers, just with the 0 added in. The integers include all of these plus the negatives of the whole numbers. So like -1 and -3 and -5. And that creates the set we call Z, which represents the integers. So the natural numbers are inside the whole numbers, which are inside the integers. And all integers are also irrational numbers, so there's even a larger set. I can make this expanded even farther and include the rational numbers, which is everything you see so far, plus fractions where the numerator and denominator are both integers. So that includes 3/4, -2/5, and so on. One set nested inside the other, inside the other. And then if you also throw in the, let's see, I need another color, running out of colors. If you also throw in the pi and the square root of 3 and the e is a famous one, 1.718 and so forth. All these numbers that whose decimal patterns neither repeat nor terminate, throw them in as well, and you have what we call the set of real numbers. Again, kind of stylizing that a little bit. Among the real numbers, these guys here that are real numbers but are not rational numbers, these would be my irrational numbers. So they're the guys that are in the real number circle but not within the rational number circle. So you have nested sets, kind of like those Russian dolls, where you open up one and there's another doll inside that. You open up another one and there's another one inside that. Natural numbers inside whole numbers, inside integers, inside rational numbers, inside real numbers. And so you may wonder, with all that discussion, is this everything? Are there numbers that don't fit into any of these categories? And here I want to bring in what we've discussed recently about square roots, where we noticed that, for example, the principal square root of 16 is not a real number. By that we mean there is no real number that when you square it, the result would be -16. Put a positive number in that square, and when you square it, it'll be positive. Put a negative number in that square, like the most obvious -4. Square -4 and it's +16. You can't get -16 with a real number. So the fact that that's not a real number tells me that there are things outside all of those circles that we've looked at so far. So what is that? Well, at some point, mathematicians developed the idea of what we call the imaginary unit, I. We define I to be the principal square root of -1. Although there were other mathematicians before this who introduced the idea in one way or another, the fellow who gets credit generally for defining, discovering, inventing, whatever you want to say, this concept of I is Raphael Bombelli, and the date is 1572. So we define the number I to be the principal square root of -1. And that's not a real number, so it's somehow outside all of those circles I've already drawn. And you might say, well, okay, that's one thing, one number only. Well, what good does that do? And we'll see in a minute. But before we do that, a quick consequence of that. If we say that the principal square root of -1 is I, that means that that's the number that when you square it, you get -1. So a consequence of defining I this way is that I squared equals -1. You'll see in future videos that I squared comes up in various calculations. Whenever you see that, it's equal to -1. Now, you might say, why on earth should we talk about things that are imaginary? Actually, the term imaginary was not given to this quantity by Bombelli, but by another very famous mathematician by the name of René Descartes. He's the fellow that invented the Cartesian plane. And it was meant to be an insult, basically. This is nonsense. This is imaginary. There's no such thing. And the name kind of stuck. But it turns out that imaginary numbers are actually far from imaginary. The entire discipline of electrical engineering is built on imaginary numbers. The flow of electrons through a wire is dictated by systems that involve imaginary numbers. So every time you flip on a switch in your house, you're using imaginary numbers. So the term is derogatory and it kind of stuck, but it is actually far from imaginary. So again, it looks like we've just introduced one number, and what difference does that make? Actually, though, once we've defined that one number, that one special number, we can talk about an entire set of numbers called the set of imaginary numbers. So the imaginary unit is just I all by itself. The set of imaginary numbers is the set of all numbers of the form b times I, where the b is a real number. Now, what does that allow you to do? So, for example, let's go back to this principal square root of -16, and we're going to do a little factoring here. Square root of -16 could be, the -16, the radicand, could be written as 16 times -1. And if I consider that the principal square root of a product is the product of the principal square roots, I can write that as the principal square root of 16 times the principal square root of -1. Principal square root of 16 is 4, and the principal square root of -1 is I. So you see what happens here is that we can now talk about square roots of all kinds of negative numbers by simply factoring. So this would be an imaginary number. It's some real number times I. Here's another example just to give you a little bit more of a flavor. Now, this is going to go back to another idea we've talked about with radicals. We can certainly write the -75 as 75 times -1. And you might also remember in talking about simplifying radicals that if you can write a radicand as a product of a perfect square and something else, a leftover, and then split up this radical as principal square root of 25, principal square root of 3, principal square root of -1. The principal square root of 25 is 5, and 5 times the principal square root of 3 is a real number, and it's multiplied by an I here, so this would be an imaginary number as well. Now here's an interesting thing that you'll see in future videos by by sort of convention. When you write the I at the end, sometimes, depending on how sloppy you are, it might look like the radical symbol extends over the I, which is not what you mean. So just as a matter of good taste, we usually reverse the order by the commutative law and write that as 5 times I times the principal square root of 3, so that the radical is written at the end. And you'll see much, much more about that. Okay, so we have a new set of numbers that's bigger, or outside of at least, the set of numbers we already knew about. Now, let's go even farther. We also talk about the set of complex numbers. The set of complex numbers is the set of all numbers that can be written in the form a plus bi, where a and b are real numbers, and the complex numbers are represented by a c. That makes sense? Although we often write that as more stylized C, looking like that. So think of a complex number as a real number added to an imaginary number. In fact, the real number is often called the real part of the complex number, and the imaginary part is often referred to cleverly as the imaginary part. So here's some examples of some complex numbers. This one fits the bill perfectly, 4 minus 3i. You might say, well, but doesn't the definition say it should be something plus something? Not really a problem there. You can rewrite this as 4 plus negative 3i, and then again there would be a real part and an imaginary part, as we've been talking about. So that would classify as a complex number as well. This is a complex number. The a and the b only have to be real numbers, so you could have irrational numbers, you could have fractions, anything like that. Now the next one, you'll see we would already have called this an imaginary number, but I'm going to claim that's also a complex number, because the negative 15i could be written in the form 0 plus negative 15i, and that would fit the form that we're talking about, a real number plus an imaginary number. So all purely imaginary numbers are also complex numbers. And then if you want to completely blow your mind, 7 is also a complex number, because 7 could be written as 7 plus 0i. So that means that all the numbers we've talked about really fall under a bigger umbrella, a bigger set, the set of complex numbers. Let's see how this all comes together. So I've recreated the diagram roughly that I created before, showing how the natural numbers are contained inside the whole numbers, are contained inside the integers, are contained inside the rational numbers, are contained inside the real numbers. Outside of the real numbers, you also have those imaginary numbers. Let's pick a new color for that. So my imaginary numbers are outside, and by the way, there's not really a unified agreed upon symbol for imaginary numbers, but that includes 5 times I, negative principal square root of 3 times I, any number that's a real number times I, and of course I itself. They're separate and apart. But containing everything you see, there's an even bigger set that contains all of this. All the real numbers, all the imaginary numbers, and that's the set of the complex numbers that contains everything. And included in the complex numbers are not only just the purely real numbers and the purely imaginary numbers, but any number that is a combination of a real number and an imaginary number, like that or like this. So those qualify as complex numbers as well. The complex numbers contain all of these things. So, quite amazing. Now, just to get a sense of, this is basically what we wanted to look at in this video, getting a sense of all these different sets. But just to kind of nail this home, I've got some numbers here, and I forgot something I wanted to write. And I just want to identify, just to conclude, how these different numbers might fit into all these different sets. So let's look, for example, at the number 4. 4 is a natural number. But from what we've seen, it's also a whole number. It's also an integer. It's also a rational number because it can be written as 4 over 1. Now, it's not an irrational number, but it is a real number. And it's not an imaginary number because there's no I. It's not a non-real complex number, but it is a complex number because that set of complex numbers encompasses everything we've seen so far. So the number 4 fits into all of those sets. Let's look at some others. Clear that out, but I need to remember to put my principal square root over the 11. Now, the principal square root of 11 is not a natural number, and it's not a whole number, and it's not an integer, and it's not a rational number. It is, however, an irrational number, and because the real numbers consist of both the irrational and the rational numbers, the principal square root of 11 is also a real number. Now, it's not an imaginary number, and it's not a non-real complex number, but because the set of complex numbers swallows up everything, it's a complex number. So I hope you kind of see how you can categorize these things. Let's look at 2 more examples. Keep having to put this back on. Negative 3i. That is not a natural number. It's not a whole number. It's not an integer, not a rational number, not an irrational number. It's not a real number. It is, however, a pure imaginary number. The word pure can be left off. It's an imaginary number. It is a non-real, because it's not a real number. It is a complex number. It's a non-real complex number, and more generally than that, it just is a complex number. The non-real complex numbers just exclude the real numbers. So that fits. And finally, when we look at 9 plus 5i, it is not a natural number, whole number, integer, rational number, irrational, or real number. But it's not purely imaginary because it's got both a real and imaginary part. It is a non-real complex number, and above and beyond that, like every example we've seen, it is a complex number. That's the complex number system. In other videos in this section, you're going to see how to work with complex numbers, how to add, subtract, multiply, and divide, and do other things. But this, I hope, is a solid introduction. Have a great day.